Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In this August 2025 lecture series, we are discussing about FIR filter design using window method. This video is the continuation of our previous videos. Today we are going to discuss about the classes of digital filters. We have two classes of digital filter. One is FIR, another one is IIR. In this finite impulse response FIR, it is non-recursive, and this have the form y of n, which is equal to h of 0 multiplied with x of n plus h of 1 x of n minus 1 plus etc. up to h of n x of n minus n. Here n is the order of the filter. Here the advantages are stable, and the phase can be made exactly linear. We can approximate any filter we want with the help of FIR filters. And the main disadvantage is we need a lot of coefficients and large for good performance. See here, our next one is infinite impulse response IIR, which is a recursive of the form y of n plus a1 y of n minus 1 plus etc. an y of n minus n, which is equal to b0 x of n plus b1 x of n minus 1 plus etc. up to bn x of n minus n. See here, this IIR filter is very selective with few coefficients, and the disadvantage is it is not necessarily stable nonlinear phase. And our first one is finite impulse response filters. Here, a filter whose impulse response has finite duration, which is called FIR filter. Here your input is x of n and output is y of n, and in this we have our filter function h of n. See here the output when h of n is 0 in the left side and right side, and we have values, finite values here. See here, the signals are always represented in terms of discrete, because we need to convert our analog continuous signals into discrete with the help of sampling. After that quantization or round off, we can convert those discrete sample values into digital. See here we have problems. For a given desired frequency response, hd of omega of the filter determine the impulse response h of n. Here we relate the frequency response and the impulse response by the DTFT. Here the formula is hd of omega, which is equal to DTFT of hd of n, which is equal to summation n equal to minus infinity to plus infinity hd of n e power minus j omega n. And for hd of n, IDTFT of hd of omega, which is equal to 1 by 2 pi integral minus by 2 pi hd of omega e power j omega n d omega. For ideal low pass filter, we'll get the response like this. Here our hd of n, which is equal to amplitude multiplied with omega c by pi sinc of omega c n by n. See the output. Here we have the limit minus omega c to plus omega c. The amplitude is a, and DTFT of your hd of omega, which gives hd of n at omega c equal to pi by 4. See the example, see the impulse response curve for ideal low pass filter. And we have two facts. The filter is not casual. The impulse response h of n is non-zero for n less than 0. We know that very well. The impulse response has infinite duration also. Here, this is not a coincidence. In general, the following can be shown: like a filter is casual, then the frequency response cannot be 0 on an interval. See here h of omega equal to 0. Here the magnitude and phase are not independent. They cannot be specified arbitrarily. As a consequence, an ideal filter cannot be casual. See here, our next problem is we want to determine a casual finite impulse response for an example for approximation of ideal filter. See here, with the help of windowing techniques, we know that we have rectangular window, Hamming window, Hanning window, and we have so many types of windows. Based on our application, we can choose either one. See here, our infinite impulse response ideal curve is windowed, either rectangular or Hamming, with the interval L minus L, and which provides a value h omega of n, hw of n, windowing function of our input. See here the output of rectangular and Hamming window, which is best here. See, by shifting in time, we make the signal into casual. See here, your h of n which is turned into hw of n minus l. See the difference. See the signal shifting in time. See the effects of windowing and shifting on the frequency response of the filter. See our windowing techniques. See here. See the diagram. Here in this windowing part we have hw of n which is equal to hd of n omega n, then hw of omega which is equal to 1 by 2 pi hd of omega w of omega. See the output of rectangular window and the filtered rectangular window, Hamming window, and the output of Hamming window. See the difference. Here, for different windows, we have different values for transition region and the attenuation in stop band. For rectangular, Bartlett, Hanning and Hamming, Blackman are shown here. The attenuation starts from minus 13 dB to minus 58 dB. See the output. Here, the effect of windowing and shifting of frequency response, we'll get the signal like this. Modulus of h of omega and the angle of h of omega. Here we have degrees of angle, and after that, after our limit, we have don't care conditions. See the output of our frequency in pass band. Our main thing is we have to maintain our output signal with ideal form. So based on that ideal form, based on that ideal values, we have to shift our signals, and finally we'll get a perfect magnitude and angle in degrees like this. Thank you for watching.